Okay, welcome to the last lecture of the day. Regina, the screen is yours.
So, last time I said that we are going to demonstrate another proof for the area bound on the length of the shortest periodic geodesic. So, right, so another proof for the length of the shortest periodic geodesic on a Riemannian two-sphere. This time, this is going to come through the filling radius. It was demonstrated that all the bands currently known are bound for the filling radius is V2Alex. This is n over 2 n through the volume. And so in this case, what we get is that filling radius it is just bounded by square root of area. So the proof that I'm going to demonstrate is not going to give the best possible bound that we can do at the moment, but it's easier to understand conceptually and is generalizable. So in order to do this, we're going to use the approach by Calabi and Zhou. And we will note the following, that, well, let's consider something like this. Maybe a three-legged starfish. While it is not possible to decompose this, to sweep this out by short curves in terms of the area, so here we are looking at the three-legged starfish with very long tentacles. And so if we want to sweep out this by curves, the length of the maximal curve will be over the order of the diameter. The diameter can be very big. That's very easy if we sweep this out by cycles. So if we were to allow something like this, so here, and I'll draw a picture next to it, right? I mean, we are allowing more than one component per slice. Those components can come together and form a figure eight. And then we can deform them and they become one curve. So in order to use this, we're going to introduce a space, gamma. And this is a space of special type of cycles. So those are piecewise smooth. And we have the following condition on the ends. I'll explain what it means in a second. So what we mean pretty much is that the ends must meet up. So we cannot have a situation like this. But either those two ends should come together, and so are those. Or they can come together in this way. And there is an intermediate situation, of course, as I described, where all the ends come and are identified at one point. And we introduce a distance on the space that makes, okay, so we define length, right? I mean, so we can define length as L of phi1 plus L of phi2. And right, and we sort of the topology on gamma we defined that makes L into continuous functional. So what are the critical points of L? And I think this was maybe observed by Pitts, that they are either a geodesic, a pair of geodesics, or simple, I should say simple geodesic, a pair of geodesics, or a figure eight. So something like this. Okay, so right, so just one more thing, and that is that via the Algebraic correspondence, if we consider pi1 of the space, we consider pi1 of the space of cycles, I should say, then this is isomorphic to the second homological proof. Okay, so here's what we are going to do. We are going to take our M and we are going to embed it in L infinity of M. We are Kordovsky embedding. And we are going to fill M in L infinity of M, so that the filling is a polyhedron and that it is very close to a manifold within the filling radius plus maybe some small delta. Okay, so we're going to have something like this. We're going to have M, and we're going to fill it by simply shell complex, so that in L infinity of M, it bounds P. Okay. And again, what we are going to use is Gromov pseudo-extension technique. So what we're going to try to do now is we're going to start with the identity map. And we're going to try and extend it to P. Well, we should not be able to do it. If we extend the identity map to P, that means the fundamental class of M bounds, which of course should not be possible. Okay.
So with P you mean a cone over?
It's not a cone.
No,
it's some simply shell complex within the filling radius. I mean, this is the best filling.
Okay.
Okay. This is it's not.
Just from the definition of filling radius.
So, sorry. So yeah. So how are we going to do it? Well, it is going to be at the beginning, at least, is going to be quite similar to what we've done before. We start with zero skeleton. Maybe I'll draw this picture again. Yeah, so we're going to triangulate P into very tiny simplices, also as we've done before. And so with zero skeleton, we're just not going to have a bunch of new vertices, the ones that are not on M. And so we would like to define the map on those vertices. And if you have a vertex V sub I, just going to map it to the closest vertex Wi in M. This is closest. Okay. And then we are going to, so the size of each simplex is, the diameter of each simplex is less than delta. And then we are going to do this for all the vertices. Okay. So this is Vi, this is Vj. And then we're going to go to one skeleton. And so we have something like V sub I, V sub j. And we would like to map it to something. So what are we going to map it to? We're going to do as before.
Short is geodesic.
Yeah, the short is geodesic that connects Wi and Wj. Okay, so what will be what can we estimate the length of this geodesic?
Less than the inductivity radius, the filling radius of.
No, not quite filling radius, but we have to use triangle inequality, right? I mean, so by triangle inequality, so here's the filling radius, here's filling radius, here's some small delta, right? So it's going to be, so the length is going to be bounded by 2 filling radius plus delta. And then we're going to go to 2 skeleton. Yeah, so we're going to go to 2 skeleton, right? And in 2 skeleton, we're going to have something like this. And we know where it's mapped, right? It's mapped to a curve that connects Wi with Wj, Wj with Wk, and Wk with Wi. And the total length of this curve is bounded by, well, it's 3 times this, so 6 filling radius plus 3 delta. And then again, you know, so nothing particularly interesting is, yeah, sorry. Right, I mean, so now we are going to use.
In the previous part, if you scroll up a little bit, so why will Wi be distance filling radius away from Vi?
Well, okay, so the
Vi is in P, right? It's a vertex of P.
Right, I mean, okay, so we can subdivide it so that it becomes a vertex of.
Yeah, so M is a subcomplex of P.
Yes.
And why will the vertex of P?
Okay, so let's do something like this, right? I mean, so let's map it to the closest point, and the closest point is going to be in some simplex, and the simplex has a very small diameter. And yeah, I agree. Maybe you should add some small number. You're going to find the closest vertex, and it's going to be only going to change by some small amount.
Okay.
Okay, so okay, so let's take this curve and let's try and use a length shortening. And as usual, we either get stuck on a periodic geodesic, which is good, and we get this periodic geodesic of length 6 filling radius, which is going to be less than or equal to 6 square root of a. We can actually contract it to a point and obtain something like this. And now we are going to go to 3 skeleton. And here.
And why there is no geodesic in the middle which obstruct this shrinking?
No, that can be, right? That's a good thing. So if we have this geodesic, right, then we stop and we're done, right? I mean, because we have.
The estimate with the finger. Okay.
So yeah, so there are 2 cases. There are 2 cases. Okay, so then we go to 3 skeleton, and with 3 skeleton, again we know. We know that we have something like this, right? And we know where the boundary is mapped. Okay. So the boundary is mapped. Well, we take Vi, Wi, Wj, Wk, Wl. We have 3 curves. We contract all of them. And now we get an object like this. And it cannot be, I mean, for at least one of the simplices here, So at least one of the simplices, if restrict F to the boundary of the simplex, the map should be homologically not trivial. Because if all of those simplices can be filled, then that would be a contradiction. So we're going to focus on this simplex, and we're going to construct a map. So we're going to focus on the simplex that looks kind of like this. And we're going to construct a non-contractible map into the space, a non-contractible map like this, into the space gamma. So how are we going to do it? I mean, I'm just going to draw a picture. We'll start with those points. Then we'll take pairs of points like those. So the total length of those curves is going to be bounded by 12 filling radius. Then we are going to end up with those guys. Yeah, because each of those curves was obtained by contracting the boundary of those two simplex. We are going to cancel this guy. We are going to insert this guy. And then we are going to continue here. Okay. So this gives us, and this map passes through those cycles of lengths at most 12 filling radius. And so that gives us an upper bound on the length of the shortest periodic geodesic, 12 square root of area, which is not as good as we do by co-area formula, but it's nice in its own way. Okay, so I'm going to
So are we proving here that the length of the shortest closure geodesic is less than or equal to 12 square root area? Or are we
yes,
I thought we were proving that the filling radius is less than or equal to something times.
No, that we're not proving. That was that was done in the morning. Filling radius is majorized by Orson width, twice Orson width. So any bound for the Orson width gives us a bound for the filling radius. Okay. Yeah, that we're not proving. We're using this. But it's good that you asked. Okay. Okay, so before I move on to something a little bit more interesting, I'm just going to mention something that is very, very simple but comes up quite often. And this is sort of the effective version of the topology lemma that you see at the very beginning of topology, where you say that if your manifold is simply connected, then if you have a diagon, a curve is one of the curves in the diagon will be path homotopic to another one on simply connected manifold. So I mean, so there's something like very elementary. And now we're just going to add some links to this. So suppose, and I'm going to mention it, I'm going to forget it for a while, but then I'm going to use it quite a bit. So here's what I'm going to say. So suppose we have two segments connecting points P and Q. And suppose we consider those segments as a loop. And suppose the lengths of those segments are bounded by L1 and L2. Did I say that? Yes. And suppose I contract it as a loop and it contracts to a point. I'm not using necessarily a length shortening. But let's say it contracts, this loop contracts over curves of length L3. Then I can construct a short path homotopy between E1 and E2. There is a short path homotopy here. And this path homotopy is very easy to see. Right? I mean, we can begin with E1, and we can start looking at the homotopy that contracted this original loop. Maybe I'll do something like this. That contracted this original loop to a point, we can start running it backwards. So we start growing this little loop out of here. And we continue like this until we have something. This is E1 star E2 bar in reverse, then followed by E1. And then we simply cancel E1 along itself, and we end up with E2. Yeah, does it make sense? So this is something very simple. I mean, there is something analogous where we contract a loop, but it doesn't contract all the way. Right? I mean, suppose we have something like this. We start to contract the loop, and it just contracts to loop alpha. Well, I mean, in this case, we can do a short homotopy between E1 and a curve like this, right? I mean, alpha bar star E2. Yes? So also pass homotopy over short curves. Okay, so I'm going to now switch slides and talk about some more theorems. Okay, so I have mentioned a bunch of more quantitative results. In particular, the theorem that I have mentioned is the theorem of Lyusternik and Riemann, which says that on any Riemannian two spheres there exist at least three simple periodic geodesics. So if you recall, right, I mean, we discussed the existence of one periodic geodesic, and then we talked just a little bit about the existence of many periodic geodesic, whatever many means. Now, there are obstacles to proving the existence, like in the most general case, there are some obstacles proving that there are infinitely many periodic geodesics, let's say, or even more than one. And what is this obstacle? The obstacle is that from topological point of view, when we get one simple geodesic, or when we get a geodesic that goes around itself some m number of times, you don't necessarily have a very good way of distinguishing between them. So it might seem that we are entitled to more than one periodic geodesic for topological reasons, but it can be geometrically the same geodesic, I mean geodesic that has the same image. And this is not a particularly interesting case. So when we say infinitely many, and we say, we actually mean geometrically distinct. So in this particular case, the reason that we will get three is actually because they are simple. And so because they are simple, we will not be, I mean, if we kind of establish that if topology guarantees us the existence of three distinct critical points, we can be sure that it's not going to be the same geodesic just going around it many times, because that's not possible, they're simple. So in order to do this, yeah, so as I said before, I like this theorem. I find it very useful, and this is one of the things that we are going to, this is, no, but I'm going to state what we're going to use. So the theorem that we are going to prove is the following, that if we, if we want three simple periodic geodesics, if we want to bound their lengths just in terms of the diameter, then we are guaranteed to have three of lengths at most 20 times the diameter. If we also insist that those geodesics don't have index 0, that they are not stable geodesics. The picture does not look something like this. I mean, if we say we don't want this, right, not this guy, then we have this bound in terms of diameter and area, which comes out from the paper about contracting the boundary of the disk. This is the result that I like and that we use all the time. So let's talk about the summary of the proof. So in order to prove this, right, I mean, so we have to come up with again, an appropriate space. And the appropriate space here is going to be the space of non-parameterized simple curves on the two-dimensional sphere. Okay, so I mean, in particular, what we want what we want is that if we start with a circle like this and rotate the circle by 180 degrees, we have the same object. And that's why we want that those curves are not parameterized. Okay, so we're going to consider it subspace that consists of constant curves on M, which is naturally identified with M, as we talked about before. And then we are going to consider the homology of this guy with coefficients in Z2. And the reason we are considering this with coefficients in Z2, this is sorry, because in this particular case, we will have 3 non-trivial homology classes in dimension 1, in dimension 2, in dimension 3. And in fact, we know the represent. So if we are on a round sphere, so let's say we are on a round sphere. Then one class, let me call it Z1. I'm going to describe its representative, right? I mean, so representatives are maps from S1, so in this case, right, it's a map from S1 to the space. This is one parameter family of curves, really. And this is what it is. I take a plane, so this is X, Y, Z. I take plane parallel to XZ and I just slice the sphere and obtain this class. So this is representative. This is already in Lyusternik-Riemannian's paper. Now here is the second cycle. The second cycle we obtain by taking this guy and rotating it by 180 degrees. It's going to be 2 parameter family of curves. And so this is 2 cycle. Rotate the whole picture. And these 3 is very easy to describe. They're just all circles on S3. All circles. Okay, I'm not going to draw all circles, but you have an idea. So there's 3 parameter family of cycles. So, right. So now we have a map from this round S2 to M. And those cycles, right, and this induces cycles on M. Okay, this induces cycles on M. And if we now apply length shortening, well, we hope that we are going to get 3 distinct geodesics corresponding to 3 homology classes, but there are potential problems. One of the potential problems is that maybe as we flow those families, maybe the curves will start intersecting. Okay? So, yeah?
What is Z3 again? Is all of the circles?
All of the circles, yeah. No, I mean round circles. I mean, like if you take planes and intersect the sphere.
The gray circles, you mean?
No, not only gray circles, but circles. Like, you know, circles on a plane.
Okay, so there are 3, yes, right.
Okay. So, right, so, yeah, so the problem is if we start flowing this, then maybe we develop self-intersections. We develop self, this is no good. I mean, so we started off with simple curves, but they might not stay simple. Now, Lyusternik and Schnirelman proved that no, they must stay simple, but the proof contains some errors. And that was corrected by many people. So it was corrected by Baumann, Yost, Taimanov, Grayson. And then, finally there was this flow constructed as modification of Birkhoff curve-Schrödinger flow. Where you also should, as a discrete flow, you also shorten the lengths of curves, but you shorten them a little bit differently. You cover your sphere, I'm just going to go about it quickly. You cover your sphere by balls of much smaller than inductivity radius. Then maybe your curve goes through those curves, you number those curves. And at each step, you change your curve in a ball by substituting by minimizing geodesic. And now you go from a ball to the ball, and then maybe you return first to the ball number 1, and then you continue this process until it converges to something. And again, it's either a point or a periodic geodesic, but in this case, the number of intersections does not increase. So if you start it off with something simple, it's going to stay simple. Now, another problem is that actually, maybe you have those different cycles, but they correspond to the same critical point. It's also possible. Not the one where you go around many times, that's not possible, but just the same. Well, in that case, Lyusternik and Riemann showed that there is a whole critical level. So you have infinitely many of periodic geodesics. So that's also not a problem. Okay. So now, in order to prove the theorem, let's note the following. So, unfortunately, we know those representatives of those non-trivial cycles on S2. But when we map it to M, right, so let's say we have something like this. So suppose we have something like this. Maybe I'll draw this representative a little bit differently, okay? So, this is cycle 1, right? What's going to happen with those curves under F? Well, I don't know. Maybe the image is going to be very long, okay? At least it's totally unclear of how we can control the lengths of curves in F star. I think I called it Z1. And similarly about Z2, etc. How do we control those lengths? It's unclear, right? So the first thing that we are going to do, we are going to start off with a round sphere. And we are going to represent those cycles by something else, by something homologous, okay? So what is it going to what is it going to be? Well, okay, so instead of this guy, this is a sphere. This is a representative of cycle 1. Yes, and then, so let's say this is, a part where the sun shines, and then there is a back part, we don't see it, but essentially the same thing happens at the back, right? We can do something instead of this. It will look like this. We're going to choose a meridian, and we're just going to take a pair of meridians, instead of those circles. Well, you can say, well, what happens in the middle? In the middle, when it's thin enough, you can just contract this to a point. Okay? So I think it's intuitively clear. So in this particular case, it is intuitively clear that those two are homologous. Because the circles are just being stretched out. So now, if this is Z1, now it has a different representative. Okay? And so how are we going to remember? We obtain Z2 by taking those guys and rotating the whole picture by pi. Yeah, I can say that we can do a little bit better if we actually modify, we can get a little bit better bound. If we modify this even more, but I don't want to discuss it. So, so the second guy we obtained by rotating this picture by pi. Right? I mean, I cannot draw more because my picture is going to get crowded, but I think we get the idea. Right? So this is a two-parameter family of curves. And so what will this correspond? Well, I mean, so we have here fixed a meridian. So now let's rotate a meridian. Let's rotate a meridian. Let's do exactly the same thing. Repeat this procedure. Yeah. So, so this is going to be two-parameter family. I mean, what is it? What is it we're gonna get? We're going to just pairs of meridians, right? So this is Z2. This is a new guy for Z2. Now for Z3, this is not going to be intuitively clear, I think. I think, you know, the first two pictures are intuitively clear. So for Z3, where we take all the circles, right, I mean, the picture of taking all the circles, the new cycle is going to correspond to the following. It's going to correspond to going around, okay, doing this, fixing a big circle, fixing two angles, alpha here and theta in the back, and going around two meridians that make angle alpha, and then going, going around two meridians in the back that make angle theta. So maybe if I draw it separately from a sphere, something like this, followed by something like this, if it makes it more clear. So, right, I mean, it's not immediately clear why, yeah, I mean, so first of all, they kind of intersect, which we don't want, but we can wiggle them a little bit and they will stop intersecting, so that's not really a problem. I think it's particularly clear where it's coming from, but it's coming from the, the following procedure. Right, I mean, so we would like to do this, right? I mean, so we have a sphere. And we have a circle. And we do this. So first we take a plane that contains this circle. Then we move this plane, we translate this plane to the south pole. Then we intersect this plane with the horizontal plane and obtain a line. Then we kind of imagine that there is sort of like a book of planes that contain this line. Now we find two planes that intersect the sphere in two circles. One touching our original circle here, and the second touching our circle in the back. Sorry, the picture is not very pretty. Okay, so we find two circles by intersecting them with planes. So first of all, this guy is going to correspond to two circles, but then we'll do something else. I mean, for this line, we find tangent meridian, and then based on the height of those circles, we obtain this pair of meridians around our meridian we were talking about. So it's not particularly intuitive, it requires a little bit more, but this is where it's coming from. So now why do we prefer those new representatives? We prefer them for, I'm going to still call them Z1, Z2, Z3. We prefer them for the following reasons. So let's say we have a standard sphere. And this, we consider all the meridians on the standard sphere. And it is diffeomorphic to our sphere. we just need to, in order to bound the length of those geodesics, we need to estimate the maximum length of the images of those meridians. That's what we want to do. Okay. So remember the following, right? I mean, so let's also remember the following. Let's start off. So I'm just going to explain how to construct those short meridians, at least in one case. And let's recall Berger lemma. So let M be a compact Riemannian manifold. Let PQ be diameter apart. Then for all W in the tangent space 2M at P, there exists a minimizing geodesic. From P to Q. With gamma prime of 0 W greater than or equal to 0. So geodesics, they're coming from all directions when your points are diameter apart. And from this lemma, one can show that we can construct a family of geodesics between P and Q. Not a family, a set of geodesics between Q. Such that and when we look at the geodesic diagonals, gamma I plus 1, then those angles are going to be less than or equal to pi. Okay. So now what can we do, right? I mean, so remember that the goal now is just to construct a meridional sweepout which is short, just like to sweep out sphere by those families of lines, right? Our sphere, M, Riemannian sphere. So, so here's our sphere. And we start with this bunch of curves, something like this. The sphere is broken in those domains. Each of those domains, so those are disks, each of those domains are disks. And we're going to, if you want to use a diameter and area bound, we just use the theorem with Evgeny and Alex about constructing the boundary of the disk through curves of lengths bounded through area and diameter. And we know that we can contract it, right? I mean, all of those can be contracted to a point over short loops. Okay, but then remember our simple lemma, right? I mean, that means that we can construct a homotopy between all those segments in the diagon over path curves. which are also short. So this is if you want the area and diameter bound. If you just want the diameter bound, the situation there is just a little bit more complicated, but maybe I will not touch it. Okay, so I think here is a result by Isabel Beach, which is in the same style. That actually you can bound, so if you fix a point now, you can produce at each point two short simple geodesic loops. So the previous statement, right? I mean, so well, what is the difference? I mean, the topology is a little bit different, but the topological part is similar. But in order to get loops, right? I mean, so in the previous statement, we used the curve shortening, and we used curve shortening over without fixed point. And the situation was that we wanted the intersections, the new intersections, not to develop. Here in this particular case, we want to fix a point. And the new problems that might arise, that intersections might develop in the neighborhood of that point. Okay? At least it's unclear right away, it's not clear how to avoid it. So it takes some, it's an intricate process where you develop a length shortening with fixed point over simple curves. Okay, so now that we are talking about, so if you remember, right, I mean, we talked about the result of Serre, and the result of Serre said that I'm going to draw a sphere again, that at each point there are infinitely many, so if you take a pair of points, there are infinitely many geodesics connecting them, but at each point there are infinitely many geodesic loops. Okay. So if you look at a sphere, you might not see those infinitely many geodesic loops. Oh, well, I mean, if we, actually we will, but we might not see infinitely many geodesics, right? Let's put it this way, right? I mean, because all those geodesics are covered by periodic geodesic. Now, in the theorem right here, those simple geodesic loops are not going to be covered by periodic geodesic, so this is a good situation. But in general, we can attempt to bound the length of those geodesic loops as well. Now, the first result, the length of the shortest, so first question maybe, let's bound the length of the shortest geodesic loop on them. Now, does the shortest geodesic loop on them have to be a periodic geodesic?
Are you asking?
I'm asking you.
Because it might not be smooth.
Yeah, I mean, it doesn't have to be, right? I mean, so for example, here, the shortest geodesic loop is this, and it's not a geodesic. It's part of the figure 8, which is a geodesic. So we can ask to bound the length of the shortest geodesic loop at each point. And the first bounds on the shortest geodesic loops are due to Serre. And there is, I think, kind of maybe an idea that we're still using, just like in a different way, that if you can construct curves as loops, over short loops, you can construct any spheres in the space of loops over short loops as well. So all spheres are decomposed into short loops, and then all of it are constructed as loops as well. Then I'm going to be a little more specific about this. Then there was my result where I bounded the length of the shortest geodesic loop on them in terms of the dimension and the diameter. And then, we sort of, but they're infinitely many, so we wanted to bound all of them. Right? I mean, so the question was whether we can bound, is it true that for is there a function that depends on k and the diameter such that you can always find at least k geodesic loops majorized by this bound. In particular, at some point, we hope that it's going to be bounded by twice the diameter, but it turns out to be incorrect. But twice the diameter times k, of course. So we came up with this bound that there always exists k geodesics of length at most 4 and k squared d. We are a little bit unhappy that this is quadratic in k. We hope that the function would be linear in k, although we don't know whether it's true or not in general. But if we have a sphere,
What was K in this case?
K is the number of geodesics we want to get. So let's say we have, okay.
Okay.
Okay. So let's say
So with xk, and then we produce.
That's right. So on a sphere, we can get, on a two-dimensional sphere, we can actually get a linear bound. So we got 22 kd originally, but then Serre improved it significantly to 8 kd, and it is 6k times d when we're talking about loops. Okay, so I'm going to prove right now. I think I have exactly the time to do it. I'm just going to prove or indicate the proof of this easiest result, which says that. So I'm proving this that so M is a closed Riemannian manifold. Of dimension n and diameter d. Then at each point there exists a geodesic loop. Of length at most. Okay, so this is, I'm going to give an indication of a proof because actually I'm going to do it for a specific case, right? So M is going to be Riemannian sphere. But it is going to be, I think it's going to be very easy to see that the same procedure can be done for an arbitrary closed Riemannian manifold. Okay, it's just, to save time. So the proof is going to be by pseudo extension. So let's say we have a diffeomorphism from S3 to M. Then we are going to try and extend to D4 triangulated as a cone over a small triangulation of S3. Okay, so this is S3. And we have a map. And we have a map to our manifold. And again, so we start with zero skeleton. So just one additional vertex, P, and where are we going to map it?
To the base point of it.
Yeah, I mean, so we want, so maybe let's call this P tilde, right? I mean, so we want to get a short loop at the point P, so that's exactly where we're going to map it. Okay. Now we're going to go to one skeleton. And okay, so here we have edges of the form. Where are we going to map it? So minimizing geodesic. Okay, so so this is EI. Okay, so now we have, let's see what this is. This is mapped to a closed curve. Okay, so what are we going to do with this curve? Sorry, yeah. So each of those curves have length d. We contract it, but we want a loop, so we're going to contract it as a loop. So either it contracts to a point, or we get, oops, or we get a geodesic loop of length bounded by 2d plus delta, and we will eventually let delta go to 0. So that's a good case. Now we go to 3 skeleton. Now we have something like this. And we know how to build this guy. There is a tiny simplex here. As before, I'm going to treat it as a point. We connect by 3 edges. We contract each of this as a loop, and at the back as well. And now to extend to 3 skeleton, we would like to produce a 1-parameter family of spheres that start with our sphere. So let's call this as 0. Okay, and ends with a point. Or, as an abstraction, we would like to get a geodesic loop. So what do we do now? So we know the following. We know that by our very, very simple observation, so here is E1, and here is E2. So by our very, very simple observation, if we can contract this loop, and this loop is contracted via curves of length 2d plus delta, then there is a path homotopy between E1 and E2 over curves of lengths, I'm going to call it E tau, and length of those curves is bounded by 3d plus delta. I might drop delta. I want to talk about it. Okay, so now, right, so I would like to construct this family of spheres. So what I'm going to do, I'm going to slowly replace E1 by E tau and repeat the whole procedure. So this is my sphere at type tau. I'm going to take points P, I'm going to take points Q, I'm going to keep E2, I'm going to keep E3, but instead of E1, I'm going to use E tau. And so I have points P and Q connected with 3 curves. I can consider 3 pairs of curves and can contract them to a point as a loop. If I get stuck in a geodesic loop, then I win. So this is geodesic loop. So either I get a geodesic loop of length 4D, or each of those curves contracts as a loop, and I get a sphere. And so I have a family of spheres that start with my sphere and end with sort of this degenerate sphere, which is glued from 2 same disks, where I can contract each pair of curves over themselves. So one might ask, as before, why those spheres change continuously. It's because in the absence of critical points, those things are continuous. So, so this is how we extend to the 3 skeleton, but that's okay, right? I mean, we need to go to 4 skeleton. So in the 4 skeleton, we get something like this. Right? And again, we know where the boundary goes from the previous step, right? From the previous step, the boundary goes to a 3 sphere. And the 3 sphere, you know, we take points P and Q, we now connect them by 4 segments, okay? And this whole procedure that we done on the previous step, we repeat, right? Means first we build the disks, then we build the 2 disks, then we build the 3 disks, as in the previous step, right? So what should we do now? Well, I mean, we are going to do exactly the same thing. I mean, we know that, so this is E1, this is E2, E3, E4. So we know that there is a short homotopy between E1 and E2. And we are now going to continuously replace E1 with a tau. And this whole procedure that was built on the previous step of the induction, we're going to repeat it. But each time you go from skeleton to skeleton, you add 2D. So, so notice that we kind of moved from dimension 2, and hopefully, you know, we're going to keep it this way, and tomorrow we're going to talk about curvature bounds. Okay, I'm going to stop.